Hello everyone, we are on page 18, okay? And we're covering topics 9.8 and 9.9. This is everything to do with chemical batteries producing electricity from a chemical reaction. These chemical batteries have a couple of names that you might see. One is called galvanic, and one is called voltaic. Okay? So galvanic cells, which is just a chemical battery, or a voltaic cell is a chemical battery. Okay? Galvanic, voltaic, and electrolytic cells. All right, great. Now, we're going to be learning about what the cell potential, like the voltage that's created by these batteries and how that relates to Gibbs free energy. That's the second part of this. That's a smaller part. Before we dive into this though, these like galvanic voltaic cells, these chemical batteries, the reaction that's happening within these chemical batteries are redox reactions. So let's do a quick little reminder about our redox. Oops. Redox. Okay. Reduction oxidation. All right, so Leo the lion says grr. Okay. Leo the lion says grr. Losing electrons is oxidizing. Okay, so if we're losing electrons, then we're oxidizing. If we are gaining electrons, then we're reducing. Okay. If we lose electrons, then the oxidation number increases. And if we gain electrons, then the oxidation number decreases or reduces. Like, that's the idea. That's why we're calling it reduction. These oxidation numbers, which is where we're tracking electrons, who has them, where are they going, the oxidation number of a species of an item is going to decrease or reduce when we gain negative electrons. Okay, so I'm going to be talking a lot about, like, hey, this is reducing and this one's oxidizing, and you need to know what I mean by that. So losing something, if something loses electrons, it's oxidizing, and if something's gaining electrons, then it's reducing. We can see reduction half reactions as well. Oxidation half reactions do occur, but we usually write them as reduction half reactions. And so that would be like, what if I have aluminum solid and we're going to add 3 electrons to this? Okay, that would turn into, oh, I didn't pick the good one. Sorry, let's do not. We're going to take aluminum solid and it's going to lose those electrons. So aluminum solid, it's going to turn into Al3 plus aqueous, probably aqueous. And it will have lost, not gained, it will have lost those 3 electrons. Okay. Now let's decide if this is an oxidation half reaction or a reduction half reaction. When something is in its pure elemental form, it has an oxidation number of 0. And if something is an ion, then its charge is the oxidation number. So we just went from 0 to a +3. Oh, oxidation number increased, and it did this by losing electrons. So this is an example of an oxidation half reaction. What if we flip that around though? What if we take aluminum 3 plus, that ion, and we add 3 electrons to it? Then it would turn into aluminum solid. And so now we're going from +3 to a 0. Oh, so we reduced. So this would be a reduction half reaction because it's gaining those electrons. All right, perfect. Here is a diagram for these chemical batteries, these cells, okay? And I have a way of remembering that oxidation happens at the anode and reduction happens at the cathode. And what you'll often hear people say in chemistry is red cat and ox. And so reduction happens at the cathode and ox. Anode oxidation. So reduction happened at the cathode, oxidation happens at the anode. All right, cool. So how we can decide if something is the anode or the cathode within a battery, it's the metal that is either gaining or losing the electrons, okay? So as a reminder, if something is oxidizing, then it's losing electrons. And if something is gaining electrons, then it's reducing. And notice, we're going to dive into why this is happening, but notice the flow of electrons in this wire. The flow of electrons, the electrons are leaving the anode, and they are being gained by the cathode, okay? So the anode, which is oxidizing, is losing the electrons, and the cathode that is gaining the electrons is the one that's reducing. So we are losing electrons. The zinc metal is losing electrons. That's what makes it the anode. And then the cathode is gaining electrons. That's what makes it the cathode. It's being reduced by gaining those electrons. All right, great. Flow of electrons is voltage. Like if we can get electrons to move, then that movement of electrons creates electricity, is our voltage. And so how a chemical battery works is really, really interesting. So you're going to have two metals, okay? So this one has, and they got to be two different kinds of metals. We'll dive into why in a little bit. So I need two different kinds of metals. So one that we have found works really good is zinc and copper. Okay? Have you heard of lithium batteries? I bet there's lithium inside that battery. So we have zinc and we have copper. And we need to take these metal chunks, these rods of metal, and place them into salt solutions, ionic solutions. We need cations and anions inside these solutions. Now, this is not a requirement by any means, but often they are put into solutions that have the same ion as the metal. So if the zinc sulfate, if this is aqueous, then that means floating inside of this solution, we have zinc 2+ ions, and we have sulfate SO4 2- ions, okay? Over here, the copper sulfate, we must have copper 2+ ions floating around, and then we'll have sulfate SO4 2- ions. Those guys are floating around. All right, wonderful. So how does this work? We take the one metal and we're going to connect it to the other metal with a wire. Okay? The electrons are going to flow through this wire. The common misconception is that people think that electrons also flow through the salt bridge. It's actually not complete in this way. Electrons don't travel here, 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 and then around. Okay, that's a really, really common misconception. The electrons are actually they're flowing here through the wire, and we have ions that are going to be flowing through the salt bridge, and the movement of these ions is what facilitates the movement of the electrons, but is not actually movement of the electrons itself. Now, what we have going on down here is that this zinc is going to, like, here's my zinc atom, okay? Zinc solid, and obviously this is so much bigger than what they actually are, but just so you can see it. So this rod is made of a whole bunch of these zinc solid atoms. They're neutral. They have, I'm looking at zinc on the periodic table, they have 30 protons, they have 30 electrons. Okay, now these zinc atoms, some of these zinc atoms, let's just do one for now, is going to leave. It's going to pop off and become zinc 2 plus in solution, okay? And so it lost 2 electrons. Well, where did those 2 electrons go? They're no longer with it. Those electrons traveled up the wire. So these 2 electrons are traveling up the wire, and they travel up and around and back down until they get to the copper. And so we're getting a gathering of electrons. Let's do 2 of them. We're getting a gathering of electrons in the cathode, okay? And so now what happens is you're going to have these copper ions that are in solution, right? So they're floating around. Well, guess what? This positive cation is attracted to those negative electrons, and they're going to combine. So this copper atom is going to, that was floating in solution, is going to land on, is going to connect to the solid copper. And the copper 2 plus will combine with the 2 electrons, and now all of a sudden you're going to have a brand new solid copper atom that's attached to the cathode. So zinc metal is leaving the anode, and copper metal is attaching to the cathode. So over time, the anode will reduce. Let's see, that's not helpful because of the word reduce for the cathode. Maybe, can I think of decrease? Let's do decrease instead of reduce. It will decrease in mass. Like the actual solid is actually going to be decreasing in mass because it's losing those solid atoms off into the solution. They're becoming aqueous ions in the solution. And the cathode actually increases in mass. It increases in mass over time, okay? Now, the problem is, though, that in this beaker over here, we are losing these cations, right? Like all the cations, all the positive ions that are floating around in this solution, they're being attached to the copper. So they're falling out of solution, right? They're becoming solid onto the copper. This is also how like metal plating works. More on that later, though. And so they're attaching to this copper. So we're getting an uneven balance over here, where there's no longer positive ions, and then there's leftover negative ions. Okay. We get the opposite that happens here, that we are gaining a bunch of the positive ions over here, and the negative ions aren't getting any higher or lower, but they're not getting any higher. So we're going to get way too many cations over here. We're going to get way too many anions over here. So what if we build a bridge so that they can travel back and forth? And we call this a salt bridge because we know how salts are just ionic compounds. And so this will facilitate the movement of these things. That cations are cations. Here's an example of one. Our cations can travel up through here and over here because we need cations over here. And then our anions can go back this way so that we can gain more anions on the other side. And so we can get this back and forth. This allows us to make this exchange so we can even back out so that we don't run out of cations and we don't become super saturated with our cations over here, right? We can balance it by adding anions into this one, and we can balance it. And the movement goes both ways, meaning can we gain cations and anions in this bridge? Absolutely. Can we lose cations and anions from the other sides as well? for sure. So this creation of these cations and latching on will stop early if we don't have a bridge in which these ions can travel through. Okay? It eventually will stop though, and the main reason why is we either run out of cations completely, but that's usually because this bar is gone. That like this will lose mass until it's gone. The cool thing is that the voltage won't change until that happens. So if we break this somehow, like if we cannot connect, if the electrons cannot flow or the ions cannot flow. So if electrons are not flowing or ions are not flowing, voltage stops. It becomes 0. But if they are flowing, even if I reduce this mass but there's still some there, or I add mass here and there's still some there, no impact on the voltage. The voltage will be the same until we've completely lost this guy, or something else has happened, like we've removed the salt bridge. But it's really important that there's something in place here that allows for ions to travel between it. Okay? They often will add some kind of like salt solution inside of usually porous material, and then they'll put this in here, and so that way the liquids and the ions with the liquids can travel between them. A lot of questions on the practice problems say, hey, what if we replace this salt bridge with wire? That doesn't work because ions can't travel through a wire. Electrons can, but ions can't. And so that breaks the circuit. The voltage will be 0 if you replace the salt bridge with a wire. We need ions to flow here. We need electrons to flow there. All right, great. We're actually going to save this page for class so we can do a little review before we jump into the new stuff. And so here's what I want you to know. Metals will have this cell potential, okay, like the reduction potential, that if a silver loses an electron, like this is, and becomes solid, this is the potential voltage from that interaction, okay? And so cations, red cat reduction happens at the cathode. And so what tends to occur is that this reduction, we want it to be really positive at the cathode, and then we want the opposite of that. We want it to be negative at the anode, right? And so here's where we get this calculation from. To get the entire voltage or cell potential of a battery, you would take the cell potential of the cathode, the thing that's reducing, and you minus it from the cell potential of the anode. And we want the most positive voltage, okay? Like 0 voltage means electrons are not flowing anymore. So if you ever do a calculation and you get a negative voltage, it doesn't mean that we're like flowing backwards. It's just not occurring. It's 0. Even though it's like if you get a negative number, it's like, no, there's no voltage there. It's just not happening. But a positive voltage means, yeah, electrons are flowing. And the greater that flow, the higher the voltage will be. And so how could we, when we know that it's E cell and it's going to be the metal that is reducing, aka the cathode, and you're subtracting it from the metal that is oxidizing, from the anode, and we look at these two here, we want the most positive voltage possible. So if our E cell is the E of the cathode minus the E of the anode, and these are our E potentials here, we want this to be the biggest number possible. So let's put the plus 0.34 volts right here. And then let's minus it from the negative 0.25 volts right there. So if we make copper the cathode and we set it up where nickel is the anode, then we're going to get a battery that has a voltage of 0.59 volts. And it really is that simple, folks. Like, you just take the most positive number and you subtract it from the most negative number. And that's what will tell us which one's the cathode and which one's the anode. What I need you to know, though, is it doesn't matter what the multiplier is on these reactions at all. Like, we know that the cathode, so this copper, Cu2+, plus 2 electrons. So there's my reduction half reaction, okay? Aqueous and solid. That if I'm going to take my reduction half reaction and I'm going to add it to my oxidation half reaction. This is currently reducing, right? It's gaining electrons, so we have to do the opposite of that. So it's going to be nickel solid turns into nickel 2 plus 2 electrons, okay? So it doesn't matter the number of electrons, or if I needed to multiply. I didn't, because it was gaining 2 electrons and losing 2 electrons. So I didn't have to multiply either of those. But even if I did, it wouldn't change the voltage on this. The overall net reaction, though, would be copper 2 plus, nickel solid turns into copper solid, and nickel 2 plus. Okay, let's see if we have another example of this, because it would be helpful. Yeah, I like this next one. Let's do this one. So, we're going to create a voltaic cell, and we want it to function as best as possible, right? We want the highest voltage. So our potential for our cell, for this battery, is the cathode minus the anode. Cathode minus the anode. And so for us, what would be best would be if silver, 0 volts, if silver was our cathode and nickel is our anode. Because if we did that, then we would get a battery, an E-cell, with a voltage of 1.05 volts. Hopefully I did my math right there. Okay, cool. So this battery would have a 1.5 volt battery. How does this exchange occur? Well, if the silver is reducing, okay, we're going from +1 to a 0, right, solid. If the silver is reducing and the nickel is oxidizing, we would need the same amount of electrons being gained that is being lost. So I'm going to take this silver reduction reaction and I'm going to multiply it by 2. 2, 2, and 2. And I need this to be done because I need the same amount of electrons being gained or lost. So my overall reaction here would be 2 silver aqueous ions plus nickel solid turns into 2 silver solid plus 1 nickel 2 plus aqueous. This is my overall reaction, my redox reaction. And even though I multiplied this by 2, I do not multiply this by 2. This is the voltage of this reaction, of this battery. Okay? All right, last concept. when we have a battery, a voltaic cell that has an E value, right? The actual battery itself has an E value that is greater than 1. Greater than 0, I mean, like it's a positive number, then that means this reaction is happening and it's thermodynamically favorable. Another way of saying thermodynamically favorable is that delta G is negative. So whenever your E cell is a positive value, then the reaction does in fact happen, and we'd say it's thermodynamically favorable. If the reaction has an E cell that is less than 0, it's a negative value, then this reaction doesn't happen. We have a delta G that is positive. Electrons do not flow. You don't have a negative voltage, you actually have a 0 voltage because this reaction is not happening. Okay. This equation is in your blue reference guide. And so it says delta G is equal to negative N. This is the number of electrons transferred in that balanced equation. Okay, so if we were doing this equation for this guy, the number of electrons that it's transferred is 2 moles of electrons. So it is negative times by the number of the moles of electrons, so for the last one it would have been 2 moles, multiplied by F, which is Faraday's constant, and that is 96,500 coulombs per mole of electrons. More on coulombs later. That is our amperage unit, yes. And then the voltage of the cell, this E cell value. Hey, we've seen this quite a bit. This like naught value up here, and this value up here, like whenever there's the naught, that means it's standard, okay? Like standard temperatures and pressures. So this is typically 25 degrees Celsius, like 298, something like that, Kelvin, and 1 atmosphere of pressure. And so when you just see those little like raised to those circles, that just means it's happening at the same temperature, in the same conditions, same pressure. All right, great. We're going to find delta G and the equilibrium constant. In case you know, we're not going to do that part because that's no longer part of it. You don't have to do those calculations anymore, but we are going to do these delta G calculations for the following reaction. So I have this reaction here, but how many electrons are actually transferring for this reaction? And we also need to know what the E cell is. So the E cell, okay, we want the most positive. I don't have a positive number, but I want the most positive minus the most negative. So if I take the negative 0.744 volts, oh my goodness, volts, which was the chromium, and it's cathode minus anode. So the cathode is going to be chromium, and I minus it from the negative 1.18 volts. So this is our anode, and it is going to be the manganese, not magnesium, manganese, Mn. The anode is here. This will tell us our E cell. Okay, we're going to be quick. We're almost done. So negative 0.74 minus our negative 1.8. So our cell has a voltage of 0.44 volts. All right, great. What is the amount of electrons transferred, though? Because we're reducing this chromium, Cr3 plus 3 electrons turns into chromium solid, and we're oxidizing our other guy, so this is going to be Mn solid turns into Mn2 plus 2 electrons. Oh, and we need these electrons to be the same. So when one is odd and one is even, we can multiply them. So since this has a coefficient of 2, I'm going to multiply everything by 2. So 2, 6, 2, and then I'll multiply everything by 3. 3, 3, and 6. And so what's canceling, what's transferring is 6 moles of electrons, and we're left with the overall that we saw up above. 3 of the Mn solid plus 2 of the chromium 3 plus results in 3 of the Mn2 plus and 2 of the chromium solid. So when I'm thinking back to this reaction, we are going to figure out what delta G is. We know that N was 6 moles of electrons. F is Faraday's constant, 96,500 coulombs per mole of electrons, so that will cancel, times by the voltage of the E cell, 0.44 volts. So without even running this number, it's going to be a negative number, right, people? A positive times by a positive times by a positive, turn that into a negative, we're going to have a negative delta G. This reaction will happen. It is thermodynamically favorable. I'm sorry I went over my time. Thank you guys so much.